Well, hello students, it's Mr. Rich. This is our recording for December 8th. Since I'm not able to do this live, I did want to make a recording for Unit 5. And so I do have some questions that some students sent in that I'll get to here in a little bit. But I first wanted to start with the first derivative test. Now we have defined critical values, or what we call critical numbers of a function f, to be any values of c, x equals c, that would make the derivative of the function 0, or that would make it undefined, so long as the value c is going to be in the interval, or I should say is going to be in the domain of the function. So if we can find values of c, which is x equals c, obviously, that would make my derivative 0, or that would make it undefined, then those are going to be locations of potential relative extremes. So this is the official definition of the first derivative test, that if we can find these values of c, and if my f prime changes from negative to positive at c, then that means there has to be a relative min. And if it changes, if the derivative of the function changes from positive to negative, that means the function f of x has a relative maximum of f at that particular value. Let's just take a look at these diagrams. So this says if f prime doesn't change its sign at the critical value, then there is neither a relative min nor relative max. So this is the picture of what really they're talking about here. That you can see that this portion of a function right here has a relative minimum at an x value of c. And notice what has to be happening for there to be a relative minimum. The derivative over here has to be negative because the function has to be decreasing, and then it has to change to increasing after it reaches that point of relative minimum. So here's where my derivative was negative on this side of c. Here's where the derivative was positive on the right side of c. That, by definition, is a relative min when the function changes from decreasing to increasing. Here's your relative maximum. Here your derivative is positive. Why is it positive? Well, we know that it's positive because the function f of x is increasing. And then when it reaches this, that's where the derivative would be equal to 0, because the tangent line slope would be 0 right there. But then the function starts to decrease, which would then turn that derivative into a negative value. All right, and then here's what happens when you find a critical value. Tangent line right here is still 0. Okay, but what happens is the function doesn't turn, right? It doesn't change directions. It was increasing, it pauses, and is neither increasing nor decreasing at that moment, but then it keeps on increasing. So derivative positive means I don't have a relative extreme at that critical value. So I'm going to work now a problem using the first derivative test and show you the steps that you would use to answer a question about where there are relative extremes of a function. This says find the points. Okay, so they're saying that I need to find the x and the y values. So kind of I know that I need to not just find x values, but y values that are relative extrema for this function on the interval 0 to 2 pi. Well, what I'm going to do is I'm going to find the critical values for f of x. I'm going to take the derivative. That's going to give me 1/2 minus cosine of x. And I'm going to set that equal to 0 to find the critical values. I will move the 1/2 to the other side. I will then divide both sides by a -1. All right, and then what I want to do is find all the values of x that would make that true. So this goes back to my unit circle. Well, cosine of x over the interval 0 to 2 pi is going to be equal to 1/2 at 2 pi over 3 and at pi over 3. If you think about that on the unit circle, that's where you would see that. No, actually, that's going to be, this is first, no, we want this to be pi over 3, first quadrant. And then down in the second quadrant, excuse me, down in the fourth quadrant, that's going to be at 5 pi over 3. Right, so you're picturing your unit circle. Right, so we're talking about first and fourth quadrants is where cosine is positive, here and here. Those are those 2 points right there. So what I'm going to do is I'm going to do a number line test. What I'm going to do is I'm going to plot these two critical values that make the derivative of f 0. And then I'm going to pick values, and we are bounded over here at 0 and 2 pi. So this creates 3 intervals, and I want to know what my function f of x is doing, whether it's increasing or decreasing in these 3 intervals. So I'm going to pick some test points. Something that would be between an angle between 0 and pi over 3 could be pi over 4. Here, we'll just use x equals pi, right? That would be between pi over 3 and 5 pi over 3. And then here we could use 7 pi over 4. Sorry, put that up here. So that's going to be my third test point. That would represent all the points that are in the interval 5 pi over 3 to 2 pi. And then what my job is here is to find out what is f prime of x for those 3 intervals. So what I'll do is I will go back to my f prime. Here is my f prime. And I do want to plug in pi over 4 right there to see whether the derivative is going to be positive or negative. So what will happen here? When I stick a pi over 4 in for cosine, that's going to be root 2 over 2, right? So this would be 1/2 minus root 2 over 2. And that's going to be a negative value. But as soon as I get past, when I get past pi over 3 and I'm using x equals pi, well, what is cosine of pi? Cosine of pi is over here is a -1. So that turns that positive. And then when cosine is 7 pi over 4, it's once again root 2 over 2, and that's going to give my derivative a negative value. And so that allows me to know what the f of x is doing. That means if its derivative was negative, it was decreasing. It reached pi over 3 where the derivative was 0 and it had a horizontal tangent line, and it changed to increasing. And then when the derivative changed to negative, it was decreasing. So then I can see that I have a relative minimum at that critical value, and I have a relative max right there. And so then I would say on a free response question, I would say something like this. F of x has a relative max at, now I am going to give just the x values here for time's sake, but at pi over 3. Because f prime of x changes. And what did it change? How did it change? It changed from being negative to positive. That's the justification for there to be a relative max. And then I would say f of x has a relative min at x equals 5 pi over 3. Changes from positive to negative. And that's how you answer those free response questions. All right. Now, they did say that they wanted the points. So really, to get credit here, to get full credit, I would plug the pi over 3 back into the original function up here and get the y value. So, but we're going to save some time and not do that. All right, let me go to the next lesson, which is finding absolute extremes on a closed interval. All right, and these are the steps that you would take to, if you have a closed interval, and it is called the extreme value theorem. And this helps us find extreme values, maxes and mins, over a closed interval a to b. So in other words, we're not trying to find relative extremes. We're trying to find global extremes over a defined closed interval for a function. And the extreme value theorem says that if your function is continuous over a closed interval, then there must be at least one absolute maximum value for the function and one absolute minimum value for the function. And this is how you would go about finding those. So what we would do is, if we are working with a closed interval and we've confirmed that the function's continuous over that closed interval, then we would proceed to find the critical numbers for the function that are in the interval of interest. We would then evaluate f at each of those critical numbers, and we would also evaluate f at each of the endpoints of the interval. So this is called the candidates test, these two steps right here, because what we're going to do is make a list of candidates where the absolute extremes might occur. Those candidates are either the critical numbers, well, the candidates are both the critical numbers and they are the endpoints of the closed interval. So the least of those f values that we just calculated would be the absolute min, the greatest would be the absolute max. And point of emphasis here, the actual max or min is a y value. Where it occurs would be an x value. So you want to pay attention to these problems. What is it asking you? Is it asking you for the x value where the maximum and min occurs, or is it asking you for the value itself? Most of the time they're asking you for the value. But let's do an example of this. This is to find the absolute extreme of this function on this closed interval. Use your calculator to sketch the graph and verify. Well, what I can say is that's a polynomial, right? So I do know that f of x is going to be continuous because polynomials are continuous over the interval -1 to 2. So by the extreme value theorem, I know that there is going to be an absolute lowest and an absolute highest value over this closed interval right here. Well, here is what we're going to do. We are going to find the critical values of our function. That is our derivative. We will find the critical values by setting it equal to 0. I will factor x squared out. I'm going to factor a 12x squared out. And now solving this, I'm getting x equals 0 and x equals 1 for my two critical values. So now, and are these both in this interval? They are both in the interval from -1 to 2. So what we will do is make our list of candidates. Well, our two critical values that happen to be in this interval are part of our list of candidates. And then we will also throw in the two endpoints, -1 and 2. So what the extreme value theorem tells us is that the absolute max or mins are going to occur at one of those 4 points over this interval. Okay, then what we do is we would plug each one of these candidates back into the original function, right? I'm not plugging them back into the derivative. I just want to know what the y value is of the function at these particular values. F of 0, that's pretty easy. We would go back and plug the rest of those in, and this is what we would get. And therefore we can see that there is my my absolute or global minimum, and there is my absolute maximum right there. Okay, and we're not going to graph this, but if you do graph this, it's a good exercise to do that. You can do that over in Desmos to do it quickly, just to confirm that, yeah, this does make sense. When you look at this interval from -1 to 2, that's where my absolute mins or maxes are. So if you go into Desmos, what you want to do is graph three things. Graph the function itself, and then graph the vertical line x equals -1 and x equals 2. So you'll be able to see more clearly the interval of you'll see the in-between parts, and you can confirm that, yeah, it's at this critical number that I had the absolute minimum, and this endpoint is where, right, because 2 was our endpoint. At that endpoint is where we had the absolute highest y value for the function. All right, so that is that's the absolute, I should say the extreme value theorem on how we find absolute extremes over closed intervals. All right, let's talk about concavity. Second derivative is what tells us about the concavity of a function. The definition of concavity. The graph of f is concave upward on an interval if f is increasing on the interval. If f prime is, that's supposed to be an f prime. If f prime is increasing on the interval, and it's concave down on the interval if f prime is decreasing. Okay, now what does that mean? It's worth maybe discussing that. So if we have some sort of polynomial function, like a third degree polynomial, you can tell here that there's going to be a point of inflection about right there. And by inspection here that this is concave down over here and that this is concave up. Now, and this is f of x. Now, what are the slopes of the tangent lines doing? On a concave down, the tangent line slopes are decreasing, because you can take a look here. I've got positive slopes here. I reach a 0 slope up at the relative maximum, but then as soon as I get past the maximum, all of those tangent line slopes turn negative. So this means here on a concave down region, what is happening is that f prime is decreasing, because if these tangent line slopes are decreasing, that means the function f prime, which is the value of those tangent line slopes, it has to be a decreasing function. And over here, you'll notice just the opposite, that my slopes go from negative to 0 to positive and more positive, higher positive as I move to the right. So this tells me that any region where f prime of x is increasing has to be a region for which the original function f of x is concave up. Well, let's go one step further. If f prime is decreasing, what must then the second derivative be doing? The second derivative must be negative, right? Because if f prime is decreasing, its derivative must be negative. Its derivative is f double prime. If f prime is increasing, then that means f double prime has to be positive. So we draw conclusions about f of x based on the value of the second derivative at any particular x value. So I know that at this value over here at c, f double prime, the second derivative of f of x, has to be a positive value, because that is in a region of concave upward. And so that is that's what we're using here on this section. Now, what about the place where the concavity changes from down to up or up to down? Well, we've learned that that's what's called a point of inflection. So points of inflection are where the concavity changes And we find those potential points of inflection by setting the second derivative equal to 0. In other words, we're going to find the critical values of f prime. And that's going to be what we do in this next example. And there's some definitions there. But this says here, determine the open intervals on which each graph is concave upward or downward, and then state any points of inflection. So our job is to find the second derivative first. So we will take the first derivative, and then take the second derivative, the derivative of the derivative, and then we will set that equal to 0 and solve it. And notice I'm solving this by factoring out 12x, and that gives me x equals 0 and x equals 2. So this just tells me that the second derivative is 0, or is 0 when x is 0 or x is 2. So I'm going to do a number line analysis like we did in the first derivative test. I'm going to put these critical values for f prime. Keep in mind, those are critical values of the f prime function. Okay, so that's what we're doing here. We're putting those critical values there. And then we want to find the sign of the second derivative. So let's use -1, 1, and 3 to represent the points that are in the intervals that are created by those two critical values. All right, well, I'm going to always determine the second derivative by using the factored form, because this factor right here would be negative when I plug in -1, and so would this one, and that's a negative times a negative, which is positive. When x is 1, this one's positive, this one's negative. That makes that a negative. But when x is 3, they're both positive. It's like that. So this allows me to draw conclusions about f of x, that it was concave up, followed by concave down, followed by concave up. So that makes the x equals 0 and x equals 2 points of inflection. So we can say here, because it was asking us, determine the intervals on which is concave up or downward, and state any points of inflection, justify your answer. So we will start off by saying this. F of x is concave up over the interval -infinity to 0 and 2 to infinity because f double prime is greater than 0. That's my justification right here. And then similarly, I won't write it, but I would then be saying that f of x is concave down over the interval 0 to 2 because f double prime is less than 0. Then finally, I would say f of x has a point of inflection at x equals 0 because f double prime changes from positive to negative, and f of x has a point of inflection at x equals 2 because f prime changes from negative to positive. The next thing I want to go over quickly is the second derivative test for relative extremes. This gives you the summary of the second derivative test. And basically what it does is this. Once we find our critical values of f of x, our c values, instead of doing a number line test, what we're going to do is we're going to find the second derivative and then evaluate the value of the second derivative at those critical values. And if the second derivative at the critical value is a positive number, it means that the f of x has a relative minimum at that particular critical value. Now, why would that be true, right? Because if the second derivative is positive, that would mean that the function at that critical value had to be concave up. And if it's concave up at that critical value, then that has to represent a location of a relative min. And if the second derivative is negative, that would mean that it's concave down and there has to be a relative max. A couple of downsides to the second derivative test for relative extremes. If you do go to the trouble of getting the second derivative and you get a 0 at the critical value, then the second derivative test is inconclusive. You have to go back to the first derivative test. So you really only do the second derivative test, or it only makes sense to do it if it's very easy for you to find the second derivative. If it's a polynomial, then it probably doesn't take very long unless you have to do a product rule. But if it's just a straight up polynomial, you can take the second derivative test in a few seconds, and it makes sense to apply the second derivative test. And let's demonstrate that with this example number 1. I'm going to find the critical values of f of x by setting its derivative equal to 0. I will factor out the greatest common factor. And then when I set these two factors equal to 0, those are my critical values. All right, this yields 1 and -1 as my critical values. What I'm going to do is find the second derivative. And now that I have the second derivative, I'm going to evaluate it at 0, which gives me an answer of 0. I will evaluate it at 1. That would be -60. -60 plus 30. So that's going to be negative. At -1, that's going to be positive. That would become a -1 times -60 is a positive 60, and then minus 30. So that would be positive. So this tells me then that I have a so f of x has a relative max at x equals 1, and f of x has a relative min at x equals -1. Now, I can go back and find the y coordinates if I wanted to for the relative max and min by plugging them into the f of x. I'm not going to do that. Now, here it is saying find the relative extreme. So I think I would go back and find what f of 1 and f of -1 is, and those would be my relative extreme values, and I would give those as a min or a max. Now notice they did us the favor of showing us the function right here. So you can see what's going on. This is why it was inconclusive. There's at x equals 0. That does happen to be a point of inflection, doesn't it? Because it was concave down here followed by concave up. So it is a point of inflection. But at any rate, what we would have to do to evaluate that 0 at x equals 0 is I would say, okay, let's go back to the number line test. Now, I had critical values at 1 and -1. So I'm going to use 1/2 and -1/2. And then I would determine what is my f prime of x. So now I'm coming back to my factored form of f prime up here. So when x is a negative, that's a -1 right there. So when x is a -1/2 and I plug that into the first derivative, that's going to be a negative, and that's going to be a negative. And when I stick in x equals +1/2, that's still a negative, that's still a negative, positive, positive. So that is not a location of a relative extreme because, as you can see it on the graph, the function was positive, the function was increasing, followed by increasing. And that's reflected in the fact that the derivative was positive, followed by positive at x equals 0. So I had two relative extreme values located at 1 for a max and a minimum at -1. All right, the next topic that I want to go over is graphs of f and f prime. These can be very confusing. So I definitely want you to get lots of practice in drawing conclusions about functions and their derivatives based on graphical analysis. I will post in Delta Math, I think I already have it there, but I will check when I get done recording this, that that there's going to be a Delta Math assignment in my AP Calc Delta Math that will allow you to practice these. They require lots and lots of practice. Here, they actually want us to sketch possible f of x's based on the f prime. The good exercises you'll see in Delta Math are they start you off with just trying to draw the right conclusions about a function or its derivative based on a graph. Here they want us to sketch it. Well, look, this is f prime of x is the function equals 2. So what does this mean? This means that this has to be a linear function of slope 2. So it could look something like this, passing through a rise and run of 2/1. So it could look something like that. Now, I don't know if that would be the graph, but I do know that this f of x, its derivative would have to be 2. Because if it's a linear function with a slope of 2, its derivative would be 2. Now, could it be down here? Sure. Right? It could have been this line. There's an infinite number of possible functions whose derivative would be y equals 2, but there's 2 of them. Okay, next one. Here we have a derivative that it looks like it's a linear function. Well, it definitely is linear, and therefore maybe its equation is y equals x. Well, what does this mean? This would mean that I'd be really looking for a quadratic function over here. Now notice what's happening here. To the right, over on this side, f prime is greater than 0. Since this is the f prime of x, over here, when you get to the left of 0, it's below the x-axis. So this has to be less than 0. Notice also the behavior is that f prime is always increasing, which would mean then if f prime is increasing, that means the second derivative would be positive always, and therefore f must be concave up. So that's the logical analysis, really, f being concave up. F prime is increasing, therefore the second derivative would be positive, which we know that means that f is concave up. So what would this look like? Maybe a quadratic. It could be that one. It could be this one. Right? We don't know which one it is. These are all possibilities. But remember, as long as I put my vertex at x equals 0, that's where the derivative is going to be equal to 0, which is what's indicated here by that intercept at 0, 0. And then you can see that to the right of 0, the function's increasing. To the left of 0, it would be decreasing, but it's always concave up over its entire domain. So that's the kind of analysis there that you want to do. But again, lots and lots of practice is required on these, and Delta Math is excellent for giving you lots and lots of questions for you to exercise your brain in doing this kind of analysis. So be sure to take a look at that, and hopefully your teacher is maybe using Delta Math for that. The last thing I wanted to go over here is optimization, which is lesson 5.10. And this gets to be like maybe one of the, so far in the class, one of the best applications of derivatives. And that is finding mins or maxes in a real life situation. So let's take a look at an example here as to how this is going to work. A manufacturer wants to design an open box having a square base and a surface area of 108 square inches. What dimension should the box be in order to produce a box with a maximum volume? Well, based on this picture, we know that the volume of that box is going to be length times width times height, which would be x squared times h, because the bottom is supposed to be a square. So this doesn't look like a square, but we're given that the base is supposed to be a square. So it's x by x. So that would be the volume. Now, what I want to do is I want to get the dimensions to produce a maximum volume. Well, if this is all you told me, and you said, let's make the highest volume, I would say the volume is infinity, and let's let x be infinity and h be something else. But there's a constraint that's put on this, that we can't just let the volume be infinitely large because we are limited by the surface area of being 108 square inches. So what we're going to do is we're going to come up with what the surface area is going to be. Now I'm going to draw our own box here to make this a little bit easier. So I want this box to be a square base. So we'll make it look like this. So there's my x, x, and h. Well, what this means is that the surface area formula for this is going to be what we call our secondary equation. I've got I got a top and a bottom that are x squared in area. And then the four sides are the same dimension, x by h, and there's 4 of them. So that would be the surface area for this box. And this surface area is 108. So really what I need to do is I need to apply this constraint to the volume. Okay, so what I can do is get rid of one of the variables, h or x. Now, it's going to be a little bit easier, I think, to solve this for h and then plug that in. So I am going to subtract x squared and then divide by 4x. And that's what h would be. I will now plug that out, substitute that in to my volume, and that gives me x squared times 108 minus x squared over 4x. Now that's one variable, and what we can do is we can simplify this and take its derivative. So what will this become if we multiply this out? Well, if we put the x squared on the top, this x will cancel one of those. So let's rewrite this as 1/4. And then this x that's remaining will distribute. So that would be 108x minus x to the third. Right, let's go ahead and distribute that. This would be 27x minus 1/4 x to the third. So that is my volume as a function only of x because of the fact that we applied this constraint to our formula. Well, we're now going to use really our extreme value theorem, right? I'm going to assume then, since this is a polynomial, the extreme value theorem tells me that there has to be an absolute maximum value if I pick an interval. Well, what I'm going to do is go ahead and take the derivative of this and find its critical value. So that would give me 27 minus 3/4 x squared. I'm going to set that equal to 0. I'm going to get 3/4 x squared is equal to 27. And you can see if you multiply by 4/3, that's going to give you x squared equals 36. So x has to be either a positive or negative 6. So what I'm going to do now is I'm going to do a number line test, right? I know that negative 6 can't be my answer where I have a relative extreme. But what I'm going to do is this. I'm going to say, okay, let's suppose 6, that's our critical value. Let's suppose that x was 5 or that x was 7, and let's find the value of v prime. So if we go back to our v prime, 27 minus 3/4 x squared, that would mean if x is a 5, that's 25 times 3/4. So that's going to be a positive. If it's a 7, x equals 7, that's going to be 27 minus 3/4 times 49. That's going to turn it negative. So that means the volume was increasing as we got close to x equals 6, and then it decreased. So that tells me that's going to be the dimension for x that's going to give me my maximum value. So what are the dimensions of this? The dimensions of this box, if we go back to our original equations up here, we know that x is going to be 6. And if we plug 6 into this, we can calculate what our height would have to be. So that would be 108 minus 36 over 24. So 108 minus 36 is 44, I believe. 44 over 24. So how about 72 over 24? 3. So those are our dimensions. It's going to be 6 by 6 by 3. So therefore, if I'm using the same amount of material, this is almost counterintuitive until you start using calculus, that if the amount of material, the surface area is at a fixed 108, the amount of volume that you're going to enclose in the box will change as the dimensions change, even though the surface area or the amount of material does not change. But we will optimally create a box in terms of optimizing volume when I choose a 6 by 6 by 3 if it is a square based box. Okay, so that's that. And then next we'll go over the questions that were submitted for today. All right, a few questions that were submitted that I want to go over. First question here says, find all values of x where the function f of x equals e to the 2x squared over 3x minus 4 has a relative maximum. We're going to find the derivative of this function to find the critical values. Well, unfortunately, we're going to have to use we will use the quotient rule. So we do low is 3x minus 4. Derivative of the upper is e to the 2x squared by the chain rule times 4x. So that is low d high minus high e to the 2x squared times the derivative of the low, which is 3, all over 3x minus 4 squared. Now, remember that critical values that we are interested in are going to be values of x that make the function's derivative 0 or undefined. Now, this is the derivative, and you will notice that x equals 4/3 does make this derivative undefined. However, 4/3 is not in the domain of this function, right? This function is all real numbers except for 4/3. So I'm really only looking for the critical values are going to be where the derivative is only 0, not undefined. So we're going to set that numerator equal to 0 and solve it. So what I'm going to do is I'm going to distribute the 4x through the parentheses here. So that would be 12x squared minus 16x, and that is times e to the 2x squared minus 3 times e to the 2x squared. Right, so that's just 3 e to the 2x squared. We've got this, so you can see here the common factor that I'm going to pull out is e to the 2x squared, leaving me 12x minus 16x minus 3 equals 0. Well, when I set these two equal to 0, this right here, when I set these two factors, this yields no solutions because e to the 2x squared will never be 0. So the only thing I have here is negative 4x minus 3 is equal to 0. So it looks like x is equal to a negative 3/4 is going to be my only critical value. So let's test that and see if it indeed is a relative maximum. So we will consider negative 3/4. Now, tying this back to our discussion on the second derivative rule for relative extremes, I wouldn't want to use the second derivative test because then I'd have to take the second derivative of this, which would be more trouble than it's worth. So we will use a value over here. Now we do have an asymptote here we have to be aware of. There's going to be a vertical asymptote at 4/3 over here. Okay, so I'm going to use x equals 1 and x equals negative 1 for my two test points right here. And okay, and so I need to know when is my derivative, what is the sign on my derivative? Well, down in the denominator, when x is negative 1, it doesn't matter what x is. That's always going to be positive. So let's go up into our factored numerator. When x is negative 1, this first factor will be positive, but this one up here is going to be negative 12 plus 16, 4 minus 3. So that makes this positive. And then when x is a 1, it's negative. So that means f of x was going positive and negative. So we can say for the answer to this question, x is equal to negative 3/4. So that's the answer. Now the justification is we would say it in a full sentence, f of x has a relative maximum at x equals negative 3/4 because f prime changes from positive to negative. Now flipping over to Desmos, I want to graph this, and let's just see if this makes graphical sense. So we will graph the original function, e to the 2x squared all over 3x minus 4. And did we get that right? It looks like we've got it right. No. So something strange. So I don't know. Yeah, maybe this looks like it might be correct. Oh, let's go back. There we go. Let's get that out of the way. Find our, there it is. So it looks like at, now see, this gives us a different value. This gives us x equals negative 0.1667. So let's see if we mess something up here. 3/4 is what I was expecting to see right here. What went wrong? So low, see, low D high. So we did, oh, I see what I did. Okay, let's go back here. So when I distributed, maybe you caught this as I was doing it. Yep. So what happened was when I distribute my 4x, it becomes 12x squared minus 16x minus 3. So then what I am solving is I'm solving this quadratic, because that factor is going to yield a critical value. As I said, that one will not, but this thing here needs to be factored. Well, I'm going to factor this, I think, by the AC method. So if I multiply the first and last, that's negative 36. I need two numbers that multiply to be negative 36, but add to be negative 16. And I believe, what would that be? 16. Is that right? Minus 16. Minus 16x, and then a minus 3. Yeah. 36. So for 36, we have 18 and 2 is what that's going to be. So that's going to be 12x squared minus 18x minus 2x minus 3. I'm using the AC method to factor this quadratic. I pull out a 6x here, and that's going to give me 2x minus 3. Pull out a minus 1, I get a 2x minus 3 equals 0. So this gives me a factor of 6x minus 1 and a factor of 2x minus 3. So my two critical values are a, did I get that right? That still doesn't jive with this over here. No, that does jive, because that would be a, no, it still doesn't. That'd be a positive 1/6. Let's see. So if I pull the 6x out of that, 2x minus 3, pulling the minus, okay, something's, I don't know what's going on here. Let's try this again. So when I split this negative 16, that's a plus 2. Yeah, so that's a plus 2x right there. So that makes this, yeah, plus 1. And we'll get it right. There we go. So now my two factors are 6x plus 1 and 2x minus 3 equals 0. So we just found our two critical values, negative 1/6 and x equals 3 over 2. Now, something tells me here that this might have been a calculator active problem. That's the feeling that I get about this, but we'll see. But anyway, I think we got it. And what we would do is, with our critical values, we would plot negative 1/6 and 3/2. And then we did recognize that we had a vertical asymptote at a positive 1 1/3. At a positive 1 1/3. That is 1.5. That is, so there's a vertical asymptote. So I'm almost convinced that this is supposed to be a, this supposed to, we're supposed to do this with graphing, I'm guessing. But at any rate, I end up with this being my relative maximum right here. If you choose x equals to the left of negative 1, 6, we'll go with negative 1. And over here, if we did x is equal to 0, then we would see that when x is a negative 1, this is going to be down. Let's use, this will always be positive. And when we look at our factored form, when x is negative 1, that's going to be a negative times a negative. So that's positive. When x is 0, it's a positive times a negative. Okay, so that does change from increasing to decreasing. So that is my location of a relative maximum. Okay. Let's do the second derivative test. The second derivative test cannot be used to conclude that x equals 2 is the location of a relative min or max for which of the following functions. Well, I know that whenever the second derivative is 0 is when I can't use the second derivative test for relative extremes. So we're just wondering which of these functions has a derivative of 0 at x equals 2. Well, that looks like one of them. That would be one of them. Right? No. If x is 2, yeah, that would be negative sine of 0. So the derivative here, oh, we have to go second derivative. Yeah. So the thing here is if we're using the second derivative test, we would have to then call this negative cosine x minus 2. If we take the second derivative here, that's definitely not going to be a 0. If we do the second derivative test here, that is 6x minus 12. When x is 2, f double prime of 2 is going to be 0. Here, cosine of 0 is 1, so we can get rid of a. We can get rid of c. I like d. Up here, when I take this derivative, that's going to be a negative 1/2 e to the minus x over 2. This one will be a positive. Ooh, that's a product rule right here. For the fact that I got a 0 here, I'm going to go ahead and go with answer D and not do the, if I had time, I would come back and take that as a product rule to see if that's a 0 also, but I don't think it's going to be. Yeah, so that's going to be our answer there. And I'll just show you one other thing here that you might find interesting, right? If you graphed the derivative, now let's graph x times e to the negative x e to the negative x over 2. I'm graphing the original function right here. What I want to do is I'm going to show you that you can tell Desmos to graph the derivative. And you can tell it to graph the second derivative right there. So if you take a look, this green line is my second derivative. At 2, it is not 0. At x equals 2, it is not 0. It is 0, but over at 4. Okay. So at any rate, that just confirms from a graphical standpoint, yeah, we were okay to reject this because we had found one whose second derivative was 0 at x equals 2. All right, students, we have one more problem that I wanted to add to this, and that is this one right here. We have a graph of f double prime, the second derivative of f, and this problem tells us that the graph of f double prime, the second derivative of the continuous function f, is shown above on the interval 0 to 9. On this interval, f has only one critical point, which occurs at x equals 6. So there is a critical point. Or not that is a critical point, but we know that at x equals 6, there is a critical point on function f of x, which we're not looking at. Which of the following statements is true about the function f on the interval 0 to 9? Well, the only thing we can really conclude about f of x from its derivative function is this. We could say that certainly over this interval from about 0.8 over to 9, f double prime of x is a positive function. Therefore, that means that f of x is concave up over that interval. So we can say that f double prime, we're looking at the graph, right? F double prime of 6 is certainly greater than 0. So that means at the point 6 comma f of 6, we know that since it's a critical point, that has to be a relative minimum, because this goes to the second derivative test for relative extrema, that if you do identify the location of a critical value or a critical point on your function f of x, and then you find out that the derivative, the second derivative at that critical value 6 is positive, then we said that means that it's concave up, and therefore it has to be a relative minimum. So our answer here is B, has to be a relative minimum, just for the fact that we know that the second derivative at that critical value 6 is a positive value. All right, I hope that helps. See you next time. All right, so that's all we have time for today, students. I